So let's start. So today let's discuss section 9.4. It's just a simple example of the special case, the real-time tracking system 911. The special case of this system. And here we assume the sigma p and sigma v are 0. So that is the covariance matrix of the process noise. So sigma p and sigma v are 0. So sigma v is the third state, and sigma m is the variance of the measurement noise. Okay, then you can use equation 919, okay, by using sigma p0 and sigma v0. Then you can get these three equations. Okay? Then the S is defined as sigma m over sigma a and h power of -4. So we have three equations. Then we have three unknown. So alpha, beta, and gamma. The three parameters we need to design. Then we can eliminate the variables to calculate alpha, beta, and gamma when S is given. So to solve these equations, you see we have the beta appears in two equations, and alpha and gamma, they both appear in three equations. So then we can first eliminate beta. Then how to do it? We can start from the third equation. Okay, so we can move all the beta term to the right hand side. Okay, then that will be 2 minus alpha times beta So if we remove these two terms, then we can take a square on both sides. Okay, you take square on both sides, then you can replace beta square by 2 alpha gamma. Then you replace the alpha by 1 minus s gamma square. Okay. Then let me show you how to use MATLAB to do the calculation. Okay. Then using MATLAB, so we can use MATLAB symbolic toolbox. So you define alpha s. So f will be the equation. So the r is the gamma. We assume this gamma is greater than 0. Then the alpha is 1 minus s gamma square. So then this part, okay, we have 2 minus alpha square. Then you replace beta by 2 alpha gamma. Then 1 alpha is canceled. Then you minus here. So a plus r divided by 2 square times a. Okay, so I can show you how to do it. You can do it step by step. So that is a polynomial. Okay, you just move all of them to one side, so you define the expression as a polynomial. Okay, so that should be this one. Then now you see this is a polynomial. When you do the calculation, then you can collect the term according to the degree of gamma. So this is the expression. So we can compare it to one in the book. You see for s power 3 gamma 6, s power 2 gamma 5, then we have 2s squared. Yeah, 3s squared. See here we have minus 2f squared, then minus s squared, and minus 3s squared, then plus s over 4, then here plus s over 4, then we have 6s, then here 3s minus 1 over 4, then gamma minus 1, then it's 0. Okay. Then we need to, for given s, so we can solve the zeros by solving the equation, by solving for gamma. So actually we can see if you take the gamma 0, so it's minus 1. Okay. If you take gamma positive infinity, then it is positive infinity. Okay. It's from minus 1 to positive infinity. So there must be at least one positive root. Okay. Then given this polynomial, then how to determine how many positive real roots are there? Then they can use something called Descartes' rule of sign. Okay. Then what is Descartes' rule of sign? It basically says if you have a polynomial, so this is a polynomial, then if all the polynomials, they have real coefficients, then you count the number of sign change. Okay. So the number of positive real zero is either equal to the number of sign changes of fx, or it's less than the number of sign changes by an even integer. So what does it mean? Okay. For example, in this case, so maybe we can assume, so s, if we assume s is greater than 1 over 12. So this coefficient for this term, so that is a negative term. So we have positive coefficient, then from positive coefficient to negative coefficient, this one sign change. So positive to negative, then negative to positive, we have two sign change. So then this positive to positive, then positive to negative, the three sign change. So basically it says that at most, okay, if you, according to the rule, okay, at most, okay, there are three positive real zero, okay. So at most, there are three real zero, but one possibility, so it may be the number of zero is 3 minus an even integer. So 3 minus 2, that means there's maybe possibility there's only one real zero. Okay, then actually we can, I will show you how to use MATLAB symbolic toolbox to solve this polynomial. Okay, here we define this polynomial as fs. Okay. So we can also use f. So f is a function of two variables, gamma and s. Now we assign some values for s, like the one in the book. We assign s from 0.09 until 0.01. Then we calculate, we solve for gamma. Then here we assign the I from 9 to 1. Then we time 0.01. So therefore it's from 0.09 until 0.01. Okay. We assign this value to 0. Then we solve this equation, okay, this polynomial. Okay. So we solve for gamma. Then we assign the value to r. Then we change the symbolic variable to a number. Okay, we use command double. then we assign the value to gamma. Then actually we can plot, okay? For each given s, we can plot the function. So the FRS, then you will see the 0, okay? That's the root of the polynomial, okay? Let's continue all the way down. So C, you will see the gamma value. Then you can compare the one in the book. Basically, that's the same. Okay? So we have gamma here until 1.211, so 1.211. Okay? Then you can also visualize. Okay? So this is the gamma from this is the gamma from 0.09 until 0.01. Okay, so this is all the roots.